What if I told you that differentiation is just multiplication in disguise? What if I told you that we can exponentiate differentiation? I mean, literally raise a number to the power of the concept of differentiation itself. You might call me crazy, maybe even stupid, and maybe you'd be right. But when we start to think of differentiation in this way, it'll open a lot of doors for us. Without further ado, let's get straight into it. As you're likely aware, there are many different notations for taking a derivative. Newton's dot notation, Leibniz's dy by dx notation, and Lagrange's prime notation. These notations all mean the same thing, they mean the derivative of y. Each of these has its strengths and weaknesses in different contexts, but today we'll be using Euler's notation. If Euler wanted to write the derivative of y, he would write dy like this. Okay, so what? This doesn't seem all that special. This notation is very basic. For example, it doesn't give us any information about what y is being differentiated with respect to. But this simplicity is its greatest strength. Watch what happens when I write the derivative of two functions added together. Which is just saying that the derivative of the sum of two functions is the same as the sum of the derivatives of those functions. So you were probably not amazed by that, but maybe you should have been. If I stopped you in the street and showed you this equation with zero context, you would assume that d is just some variable, a number, right? In that case, you'd think that this equation is totally obvious. That is the key insight here. The key insight is that we can treat differentiation as though it's just multiplication by a number which we've called d. With this idea in mind, let's consider differentiating something twice. We might write something like this. Again, I want you to imagine that I walk up to you in the street and show you this. What would you say, thinking that d was just some number? You might suggest that we write it like this, as d squared f. And in general, we may wish to write the nth derivative of f as d to the n f. Amazing. Okay, well, maybe not quite that amazing just yet, but let's keep going. What about integration, which is just the inverse operation of differentiation? We might want to use a new symbol, so let's use I. So the integral of f could be written as if. Since we want I to be the inverse of d, we want I df equals dif equals f for every f. Now, don't forget the key idea here. We want to treat these like they're just numbers. Again, I'm going to walk up to you in the middle of the street and show you this. I tell you that d and I are just some numbers, and that this equation is true for every f. What might you suggest would be the relationship between d and I? You might well suggest that clearly I equals 1 over d, since 1 over d df equals d 1 over df equals f. Makes sense, right? This insight that the inverse of d can be written as 1 over d is of very deep importance, and it will be one of the keystones of the core part of this video later. Before I continue, I want to note that this idea of treating d as just a number doesn't always work out so nicely. For example, if we consider d fg, we may be tempted to write this as ftg. Since we're treating everything as just numbers, the order doesn't matter. Of course, we know this isn't actually the case, unless f happens to be a constant. Instead, we should be using the product rule. The important point is that always treating d as a number can lead to some unexpected consequences, so it's important that we don't do anything too crazy. With that being said, let's do something really, really crazy. Let's try to exponentiate differentiation. This sounds like a really strange and abstract idea. How can we possibly exponentiate differentiation? What would that even mean? Well, one way to think about this is to, again, just forget about the differentiation for a moment, and again think of d as just some number. Now we can use the definition of the exponential function. For those unfamiliar, the typical definition, and the one which we'll be using, is the following infinite sum. Great. So now we have this. Let's start thinking of d as being differentiation again. Differentiation is of course something which we do to functions. Let's see what happens when we apply whatever this is to a function f. We want to see what this infinite series will do to our function f. We'll expand the brackets here. Now we're about to use what we said earlier about d to the n f being the nth derivative of f. Meaning df becomes f prime, d squared f becomes f double prime, d cubed f becomes f triple prime, and so on. It certainly isn't obvious what this is doing. Let's see what happens when we try some examples. Let's see what this whole thing becomes when we let f of x equal x, for example. The first term is just x. The second term is the derivative of x, which is 1. The higher derivatives reach 0, so the third, fourth, and all terms after vanish. And we're left with x plus 1. As a reminder of what we're doing, we were finding out what e to the d does to the function f of x equals x. It adds 1 to it. Maybe this operator, which we're calling e to the d, represents the shift up by 1, taking in a function and simply adding 1 to it. Well, let's see what happens when we try f of x equals x squared. X squared is x squared. The derivative of x squared is 2x. The second derivative of x squared is the derivative of 2x, which is 2. The higher derivatives are all 0, and so they vanish. The last term here is equal to 1. This is a lot less nice than what we had before. E to the d is definitely not just adding 1. You might notice that we can factorize the right hand side into x plus 1 all squared. So e to the d turns x into x plus 1, and it turns x squared into x plus 1 squared. It seems to be replacing x by x plus 1. We might then suggest that maybe e to the d represents a left shift on a graph by 1 unit. In other words, it takes the function f of x and turns it into the function f of x plus 1, which if you plot on the graph is 1 unit to the left of f of x. It's quite easy to show that this is the case by using Taylor series. If you want the details, I'll flash them quickly on screen now, so feel free to pause the video and have a look. We're now left with the perhaps surprising result that this strange operation of raising e to the power of differentiation gives us a very simple shift left by 1 unit. Since this operator performs a left shift, it seems sensible to represent it by the letter L for left. What then about a right shift? Can we come up with an operator to perform a shift to right by 1 unit? In other words, I want something that turns f of x into f of x minus 1. Let's call this operator R for right. Now don't worry, we don't need to do any more complicated Taylor series shenanigans to figure this one out. We'll use the idea of inverse operations being reciprocals again. Since shifting to the right is the inverse of shifting to the left, we would expect that R equals 1 over L, which is then 1 over e to the d, which we may then wish to write as e to the minus d. If you want to try and show that this works using Taylor series in a similar way to the work in which I flashed on screen before, then please pause the video and have a go. For now, we'll move away from these abstract ideas into something a little bit more concrete. But don't worry, these left and right shift operators will sneak their way back in again, so do be on the lookout for them. Let's move away now from differentiation, which lives in the world of the continuous, and turn our attention instead to the world of the discrete. You may be familiar with the fundamental theorem of calculus, which tells us how to evaluate an integral between 2 points. An integral is basically a continuous sum. If you don't know much about integrals, then don't worry, the details aren't important, but the overarching ideas will be. The tricky part is finding a function which differentiates to give us the integrand. Differentiation is essentially always easy as long as you know the rules, but integration is not always so. The motivating question with which we'll next concern ourselves is if we can come up with something like this for discrete sums. Those are just the same old sums you're used to seeing, where you just add a list of terms together. This is a regular old discrete sum, written using sigma notation. This is the discrete version of an integral. So far, so good. The fundamental theorem of calculus joins together the ideas of integration and differentiation. So a good place to start looking for a discrete analog might be to ask, what is the discrete version of a derivative? Before I answer the question for you, I want you to really think about it. The derivative tells us how quickly a continuous function is increasing at a particular point. If I have a discrete function, a function which can only take on integer values as inputs, how do I get an idea of how quickly this function is changing at a point? A good idea might be to take the difference between consecutive values. For example, if I wanted to see how quickly f of n is increasing at n equals 5, I might consider f of 5 minus f of 4, or f of 6 minus f of 5. Instead of taking the derivative, we're taking the difference of the function. Let's take a look at some examples to really get a better grip on what this difference is actually doing. Previously, we used d to represent taking a derivative. Here, I'll use delta to represent taking a difference. We'll define this difference operator by delta f of n equals f of n minus f of n minus 1. We're taking the current value of the function and subtracting the previous value. Whether we take the difference between the previous term and the current term, or between the current term and the next term, really doesn't matter. There's a very interesting connection, which I'll point out later, which arises depending on which one we choose. I'll be taking the difference between the previous term and the current one. Before we jump into the deep end, let's take a quick look at a simple example. F of n equals n. We get this, which is simply just 1. This fits well with our intuition. F of n equals n is linear, so the rate at which it's increasing does not change. This example is analogous to how the derivative of f of x equals x is 1. Another even simpler example we might consider is that of f of n equals 1, which would give 1 minus 1, which is 0. This again fits with our intuition. F of n equals 1 is constant, so it isn't changing, so the difference between terms is 0. This is analogous to how the derivative of f of x equals 1 is 0. One last, slightly more interesting example before we dive into the deep end. F of n equals n squared. Let's expand the brackets and see what happens. Again, this seems somewhat familiar. The difference of f of n equals n squared being 2n minus 1 is reminiscent to the derivative of f of x equals x squared being 2x. Now, we're finally ready to reach the goal which we've been striving for in this section. Let's see if we can come up with a discrete analog to the fundamental theorem of calculus. The objective is essentially to find a way to express the sum of the difference of a function in terms of the function, much like how FTC lets us express the integral of a derivative of a function in terms of that function. This is actually incredibly easy and turns out to be quite obvious. I implore you to have a go yourself before I reveal what's about to happen. As I write out the terms of the series, you'll hopefully notice how most of the terms seem to cancel. And this is it, ladies and gentlemen. This is what we were trying to find. It's very reminiscent of the fundamental theorem of calculus, except we have an f of a minus 1 instead of an f of a. It will end up being much easier to work with this if we have an f of a instead, so I'll just replace a by a plus 1. This is our final result. Remember, delta f of n equals f of n minus f of n minus 1. As I mentioned earlier, the tricky thing about using FTC is finding a function whose derivative is the integrand. Here we have much the same problem. We need to find a function whose difference is the summand. Going one way is very easy, going the other, it turns out, not so much. You may also wish to take a moment to appreciate the similarity between this situation and the fundamental theorem of calculus, which I keep mentioning. This discrete analogue is perhaps more obvious and more intuitive, and I hope that this insight makes the continuous case feel all the more intuitive as well. We now need to solve the problem of being unable to easily reverse the process of taking the difference. Maybe you can start to see where the ideas from the first section of the video are about to come into play. I'm calling the inverse of delta sigma. Of course, this means we can write sigma equals 1 over delta, just as I wrote I equals 1 over d in the first part of the video. So far, this isn't helpful at all. We want a more explicit form for sigma, which means we need another way to write delta. Remember what delta does? It takes a copy of f and subtracts from it a right-shifted version of f. Recall the right-shift operator r turns f of n into f of n minus 1. This means we can now write delta f of n equals 1 minus r f of n, by essentially factoring out the f of n to the right. Since delta and 1 minus r do the same thing, they're the same operator, and so we say that delta equals 1 minus r. Now we have this. Still not very helpful. Is there any other piece of information which we can use here? Think back to earlier in the video. We found that r equals e to the minus d. Let's bring that in here. Now I'll multiply the top and bottom by e to the d. Those of you who watched my last video should be getting quite excited. This function looks very familiar to something which we saw in that video. As a reminder, or in case you haven't seen it, what we have here looks very similar to the generating function of the Bernoulli numbers. Those are the Bn numbers in the infinite sum. Earlier in this video, I said there's an interesting connection that arises depending on how we choose to define delta. I defined it as the difference between the current and previous term, which gave us 1 minus r, which gave us this. I could instead though have chosen to define it as the difference between the current term and the next term. If I'd done this, we would have delta equals L minus 1, which would then have given us sigma equals 1 over e to the d minus 1, instead of what we have here. This may again sound familiar to those of you who watched the previous video, because that expression is very similar to the generating function for the Bernoulli numbers when we use a different convention. Of course, if you want to find out more about the infinite sum in the top left, and about these different conventions I'm talking about, then I would recommend that you go and watch that other video after this one. I'll put a link to that video in the description where I go into it. Our expression and the generating function will be the same if we divide the generating function by x. Of course, we have d instead of x. We now have our answer. This is all quite abstract at this point. What does this mean and how can I use it? Let's take a step back and see how we can apply it to our discrete analogue of FTC, which remember was the reason for finding this thing to begin with. As a reminder, this is what we found before. I've replaced f by sigma f. This means that the summand has gone from delta f to just f, and instead of f of b minus f of a, we have sigma f of b minus sigma f of a. It's very important to understand here that we're not applying sigma to f of a and to f of b, because those are just some constants. We're applying sigma to f, and then evaluating this as a and b, and taking the difference. This is a more compact way of writing that idea. Now we can use our formula for sigma on our top equation. We now need to apply this weird sum operator thing to our function f. I'll begin by taking out the first two terms. There are two reasons for this, which I mentioned briefly in my previous video. The first reason is that this avoids any ambiguity as to which convention we're using for the Bernoulli numbers. For those of you who didn't see the last video, there are two conventions for the Bernoulli numbers. The only difference between them is that one of them defines b1 as being 1/2, and the other one defines b1 as being negative 1/2. Here, we're using the convention where b1 is 1/2. If we write out the first two terms explicitly, we're removing this ambiguity, and everyone will agree regardless of which convention they're using. The other reason is, as I mentioned in that video, is that all of the Bernoulli numbers with odd index, except b1, are 0, which means we'll be able to skip every second term after I've taken out the first two. When I take out the first two terms, we get this. D to the k minus 1 f of n is the k minus 1th derivative of f. D to the 0 means differentiate 0 times. In other words, it does nothing. D to the minus 1 is the inverse of differentiation. We find the antiderivative, evaluate it as a and b, and then take the difference. This is the integral from a to b of f. I've replaced the n with x, simply because writing the integral of f of n dn looks a bit weird. All we need to do now is just evaluate the inside of the square brackets at a and b, and then take the difference. Great. There's one last thing we'll do to this. The odd Bernoulli numbers except 1 are 0, so the sum is effectively only counting over the even values, 2, 4, 6, 8, etc. We can therefore replace the k's with 2k and start the sum at 1 instead of 2. As a reminder of what this thing is actually finding for us, it finds the sum from a plus 1 to b of f of n. It would be nicer if the sum went from a instead of a plus 1. We can fix this by adding f of a to both sides. Wow, what a monster this thing is. This is the Euler-Maclaurin Summation Formula, derived in a totally different way than you've probably seen before, if you've ever seen it before at all. This equation really is a monster, isn't it? It also seems quite useless on the surface because we've turned an easy finite discrete sum, which is always possible to calculate by brute force, and we've turned it into an integral, which isn't always so easy, and a nasty looking infinite sum, which surely is going to be a true pain to deal with. But don't worry, we're going to wrangle it. But I warn you, this formula behaves very, very strangely. I mean, it is seriously weird. Before we get to the weirdness though, let's dip our feet in with a nice example where it behaves very well. We're going to use this formula to find the sum of the first k square numbers. If you watched my previous video, you'll know the answer should be 1/3 k cubed plus 1/2 k squared plus 1/6 k. Let's put the things at the top into our formula and see if it gives us the right answer. Before we can do that though, we need to deal with the derivatives inside the infinite sum. We need the first, third, fifth, etc. derivatives, the odd derivatives. The derivative of x squared is 2x, the second derivative is then 2, the third derivative and all derivatives after are 0. This means that all of the terms of the infinite sum, except the first, will vanish. We can now apply that f prime of x equals 2x. And b2 is 1/6. The integral of x squared is a third x cubed, and so the integral will be 1/3 k cubed minus 1/3. Simplifying the right hand side, k cubed over 3 plus k squared over 2 plus k over 6, which is exactly what we thought it should be. Our formula at least seems to be working for cases where we have a polynomial function, because if you keep taking derivatives of a polynomial, you'll eventually get 0, meaning that the sum terminates at some point and is no longer infinite. This is good news, but it isn't all that useful because we could already sum polynomials by using Fallhaber's formula from the last video, which motivated the Bernoulli numbers in the first place. To see where this sum stops working and yet somehow becomes much more useful due to its really quite strange behaviour, I'll use it to sum the reciprocals of cubes. The typical example is to use the reciprocals of squares, aka the Basel problem. But because that's already been done so many times, I'll use this different example. The integral isn't very hard. The integral of 1 over x cubed is the integral of x to the minus 3, which is minus a half x to the minus 2, or minus 1 over 2x squared. This becomes a half minus 1 over 2k squared. The fraction can be split into two terms. Finally, the hard part, the infinite sum. This is where things are about to become very strange indeed. First, we need to work out what the 2n minus 1th derivative of f will be. Do we notice any patterns here? We multiply by 3, then 4, then 5, and so on. These are almost factorials. They aren't because we started with 3 instead of 2, which means they're missing that factor of 2. The second derivative has a 12, which is 24 over 2, or 4 factorial over 2. The third derivative has a 60, which is 5 factorial over 2. The fourth derivative has 360, which is 6 factorial over 2. It seems that the mth derivative has m plus 2 factorial over 2. They also alternate between positive and negative, with the even derivatives being positive. So we'll have a factor of minus 1 to the m. Finally, the power of x in the mth derivative is x to the minus m plus 3. Putting this all together, we have the mth derivative here. If you wanted to prove this more rigorously, you could use induction, but I'm not going to bother doing that here. Of course, we actually wanted the 2n minus 1th derivative, so let's let m equal 2n minus 1. 2n minus 1 is odd, so minus 1 to the 2n minus 1 is minus 1. Putting in x equals k and x equals 1, and substituting these into our formula. We have a common factor of 2n plus 1 factorial over 2. The 2n plus 1 factorial partially cancels the 2n factorial. Now for the moment of truth. Let k go to infinity. The left-hand side becomes the infinite sum we want. Let's call it s. The 1 over 2k squared and 1 over 2k cubed will vanish as k goes to infinity. Also, k to the minus 2n plus 2 will go to 0, since minus 2n plus 2 is negative. Houston, we have a problem. This infinite series diverges. Since, as we saw in the last video, the Bernoulli numbers diverge, so this can't be right. This is what I meant when I said the formula doesn't actually work. Now don't worry, we can still salvage the situation, and use what we've done so far to find a very good approximation for the answer. You're about to see what I meant by the Euler-Maclaurin formula having some very strange behaviour, and how that strangeness is about to make it very useful. I warn you, the next thing I'm going to do might make you very uncomfortable. Even though we said the right-hand side of this equation diverges, we're just going to keep it and pretend that it doesn't, and then substitute it into our original equation. You'll see what I mean when I do it. Here is our full equation just before I let k go to infinity. Splitting the sum into two parts, we can now make our substitution. Finally, rearrange for s, which remember is our sum to infinity. This is where some of that weirdness is about to come back. Notice that the infinite sum we have here will still diverge for any particular value of k, because the Bernoulli numbers grow so quickly. As k gets larger and larger, the sum will still diverge, but it will take longer to do so. This has the effect that if we have more and more terms of the infinite sum, the closer we get to the true value, but only up to a point, after which it gets further and further away. The larger the value of k, the more of these terms which we can add before this happens. Also, the larger the value of k, the smaller each term will be, and so we should get quicker convergence. Let's see what we can do with just the first two terms of the infinite sum and setting k equal to 5. The first two terms will have b2, which is a sixth, and b4, which is negative 1/30th. When we compute this out, which would be a lot of work if we didn't have calculators, we get this, which is correct up to 6 decimal places. That might seem quite unimpressive considering the amount of work we had to do to get this answer, but we would have needed to add about 1,000 terms of our original series in order to get an answer correct to this many decimal places. If you're interested in how I figured that out, stick around because I'll show you the method I used later. As we continue to add more terms of the infinite series, we'll eventually get divergence, because as I mentioned, the sum diverges. This is only true though for a fixed value of k. For example, if I stick with k equals 5, then at some point the extra correction terms will become bigger, and the approximation will get worse as we add more terms. If I increase the value of k, for example if I let k equal 10, then this is still going to happen eventually, but I can add more correction terms before it does. One way of looking at what this formula is doing is it's providing us with some kind of correction terms. We add some number of terms of our original series, the first k of them. Our answer will be off by some amount. The formula then generates these correction terms, which will be different depending on our value of k. The correction terms then allow us to very quickly get much closer to the true answer. But don't be too greedy, because if you try to use too many correction terms for your chosen value of k, your approximation will only get worse. These correction terms are very, very powerful. When I increase k, they become even more powerful due to a variety of different factors. Firstly, we're adding more terms to our original series anyway, so our guess will be better. Secondly, we can add more correction terms, meaning we can get a better approximation by using more of them. Thirdly, the correction terms are smaller for larger k, which means they get closer and closer to the answer more rapidly. These factors combined mean that when I increase k from say 5 to 10, which still isn't that many all things considered, we can start to get a very, very good approximation for the true answer by using these corrections. As an example to demonstrate some of this formula's true power, I'll set k equal to 10 and we'll use 12 correction terms. Let k equal 10. As you can see, even with the first 20 Bernoulli numbers, which is 12 correction terms, when I let k equal 10, the last one is still incredibly small. What's more important though than the terms being small is that they are considerably smaller than the previous ones, because otherwise they'll start to undo the work which the other ones have already done for you. In this case, the last correction term is about minus 5.56 times 10 to the minus 19. The one before it is about 5.22 times 10 to the minus 18, so the last one is about 10 times smaller. We could keep going for quite some time, but what we have here should be more than enough to find a very good approximation for the answer. If we evaluate the sum on screen, I'll use a calculator because I'm not crazy, we get this number. Actually, using a calculator wasn't enough. I couldn't get this many decimal places. I had to write some Python code using an arbitrary precision library in order to calculate this value. That being said, it would of course be possible to calculate this by hand, though you would need to be very careful and even more stubborn. This turns out to be correct to 17 decimal places. This might not seem very impressive considering the amount of work we needed to do in order to get this number, but let's figure out how many terms of the original series you would have needed to add together before you got an answer this accurate. When you see how many, the work we did here will look like nothing in comparison. Finding out how many terms we would need to add until the answer is correct to 17 decimal places is basically impossible without just doing it. A much easier question, but with an answer that would be more or less the same, is to ask how many terms we need to add until we have an error of less than 1/2 times 10 to the minus 17. The reason we want an error of this amount is because 1/2 times 10 to the minus 17 is half of the 17th decimal digit, which is how far we would need to be from the true answer in order to round to that value. This isn't exact because the true value has more than 17 decimal places, but the difference is really not significant. To summarize what we're going to attempt to do, we want to find out how many terms we need to add of our original series before we get an error within 1/2 times 10 to the minus 17. This will tell us roughly how many terms of the original series you would have needed to add together in order to get an answer as good as the one which we achieved by using the Euler-Maclaurin formula. We don't know how many terms we need, so we'll call this number n. The true value of the sum s is the sum to infinity. Our approximation is the sum up to n. The error is the difference between the true value and our approximation. This is the sum from n plus 1 to infinity. What we would like to have is an easier to work with approximation of this error. Fortunately, this is quite easy to do, thanks to the fact that the function 1/x cubed is decreasing, and that it's an easy function to integrate. Considering the graph of 1/x cubed, note that the x and y axes here have very different scales. If I wanted to consider the sum as n goes from 15 to infinity, this is the same as considering the area of these rectangles, which each have a width of 1 and heights of 1/15 cubed, 1/16 cubed, etc. The total orange area here is equal to that infinite sum. Notice that each rectangle touches the curve at its top left corner. If I were to consider the area under the curve, here the black area, this is the integral from 15 to infinity. Notice that if I overlay both the black and the orange at the same time, the black area is clearly less than the orange area. This tells us that the integral from 15 to infinity is less than the discrete sum with the same bounds. An alternative way of considering the sum from 15 to infinity would be to draw the same rectangles again, but instead of each rectangle touching the curve at its top left corner, we instead make them touch the curve at their top right corners, which looks like this. The orange area here is still exactly the same as it was before. It still represents the discrete sum from 15 to infinity. The only thing we've changed is that we've shifted each orange rectangle left by 1. Notice that if we were to consider the integral from 14 to infinity, which represents the black area here, the black area is now more than the orange area was. This tells us that the integral from 14 to infinity is greater than the discrete sum from 15 to infinity, which in turn is greater than the integral from 15 to infinity. I chose 15 as an arbitrary example here. The same argument applies exactly the same for any n. This is the more general case of what we just saw, the example I just gave being where n is 14. Remember, the discrete sum in the middle of this inequality represents the error incurred when you sum the first n reciprocals of cubes. The integrals on either side can be evaluated very easily. The integral of 1/x cubed is the integral of x to the minus 3, which is minus 1/2 x to the minus 2, or simply minus 1/2x squared. Let's relabel the discrete sum in the middle to e, as it represents the error. We now have two inequalities. 1/2n plus 1 squared is less or equal to e, and e is less or equal to 1/2n squared. The first can be rearranged for n by multiplying both sides by n plus 1 squared, dividing by e, these quantities are both positive, so this is allowed, then square rooting both sides, and finally subtracting 1. The second inequality can be rearranged in a similar way. We now have an upper and lower bound for n. The upper and lower bound are very close together, which makes sense because the integrals give us a very good approximation of the sum, since for large values of n, the graph of y equals 1 over x cubed is almost flat. Since they're so close, differing by only 1, we can approximate n by using either one of them. N is approximately the square root of 1 over 2e, where e is the error and n is the number of terms required to achieve such an error. We wanted to know how many terms you would need to add together in order to get an error of 1/2 times 10 to the minus 17. If we simply let e equal 1/2 times 10 to the minus 17, we get about 316 million terms. That's roughly how many terms of the original series you would need to add together to get an approximation as good as the Euler-Maclaurin formula did in about 20. Technically, our approximation was even better than this, because whilst the 18th decimal place was incorrect, it differed by only 2 from the true digit. We can be more precise by setting the error e equal to the actual difference between the true value and our approximation. When we do this, we get n is approximately 463 million. Point being, the Euler-Maclaurin summation formula may be ugly and may not be the most well-behaved thing ever. It might take a long time to work out what the correction terms should be, and then longer still to actually add them on to your approximation. But it is still very, very useful. It allowed us to do in just over 20 terms what would have otherwise taken hundreds of millions. That is what makes this formula so incredibly useful. So that's it. The video is pretty much over now, but before you go, I have a quick bonus section for you. Last time I made a promise, but I couldn't figure out how to fit it into the video, so I'm just going to shoehorn it in at the end here instead. I'm going to derive for you the Maclaurin series for the tangent function. I'll do this by considering the exponential form. If you're wondering where this comes from, it comes from Euler's formula, which says this. By replacing x by negative x, we get this. Adding these together and dividing by 2 gives us a formula for cos x. Subtracting and dividing by 2i gives us sin x. Tan x is sin x over cos x, which gives us this. If we multiply the top and bottom by e to the ix, we get the form in the top left. The reason I want to investigate this form of the tangent function is because it has some similarities with the generating functions which we found last time. If we divide each of these by x, they become even more similar. The tangent function uses 2ix instead of x, so if we make that substitution as well, we have this. The tangent function has a minus in the numerator and a plus in the denominator. Our generating functions both have minuses in the denominators, so considering the reciprocal of the tangent function would actually be easier. 1 over tan x is cot x, so we have cot x equals I e to the 2ix plus 1 over e to the 2ix minus 1. We can split the fraction into 2 parts. We can now apply our generating functions. We have quite a lot of common factors here which we can factor out. I'll next take out the 2 to the n minus 1 and I to the n minus 1. I'll next take out the first 2 terms, as we often do when dealing with sums involving Bernoulli numbers. The n equals 0 term is 1 over x, since b0 plus equals b0 minus equals 1. The n equals 1 term is 0 because b1 plus b1 minus is 1/2 plus minus a half, which is 0. Since n inside the sum is now greater or equal to 2, bn plus equals bn minus, so we'll now just use bn. I will now solve the sum at n equals 1 and replace each n with 2n, since the odd Bernoulli numbers will all be 0. Two to the 2n is 2 squared to the n, or simply 4 to the n. I to the 2n is I squared to the n, or minus 1 to the n. Finally, notice that when n equals 0, we have x to the minus 1, which means the 1 over x term at the front is the n equals 0 term. This is the power series for the cotangent function. We wanted the tangent function. We need an identity which relates tan to cot. An obvious one would be tan x equals 1 over cot x. Unfortunately, it isn't easy to turn the reciprocal of an infinite sum into an infinite sum. Another formula which might come to mind is one which arises when considering the double angle formula for the cotangent function. In case you are unfamiliar, I'll derive it quickly now. Cot equals cos over sine. We then use the double angle formulae for sine and cos. We then split the fraction into two parts. Some cancellations. This is 1/2 cot x minus 1/2 tan x. We can rearrange this for tan x. As you can hopefully see, this identity will be much more useful in finding as a Maclaurin series expansion than using tan x equals 1 over cot x or something like that. If we apply the cotangent series to this identity, we get this. Again, we can factor all sorts here. All that's left to do now is simplify this. And there we have it. That's it for the bonus section. If you liked the video, give it a like and subscribe. If you didn't like it, leave a dislike and leave a mean comment. Thanks for watching.